Every premium leather jacket begins long before the factory floor. It begins here, on American ranch land. In states like Texas, cattle are raised not for leather, but primarily for beef production. Leather is a byproduct, but a critically important one. The quality of leather depends on the life of the animal. Open-range grazing reduces stress and minimizes skin damage, fewer scars, fewer parasite marks, stronger, more uniform fiber structure. The biology of the hide is shaped by environment, nutrition, and climate. Leather is not fabric, it is collagen, a dense, interwoven network of protein fibers. Under magnification, the hide reveals a three-dimensional matrix, a natural composite material engineered by biology. The tighter and more uniform this collagen weave, the stronger the finished leather. This is why premium manufacturers carefully select hides based on thickness, grain integrity, and fiber density long before tanning even begins. Once separated during meat processing, hides must be preserved immediately. Without preservation, bacterial growth begins within hours. Salt curing is the first defensive step. Salt draws out moisture, inhibiting microbial activity and stabilizing the collagen structure. This controlled dehydration prevents irreversible protein breakdown before tanning. Before entering the tannery, each hide is graded. Inspectors evaluate thickness, scar patterns, branding marks, and structural consistency. Why does grading matter? Because premium leather jackets require uniform panels. Variations in thickness can affect stitch tension, drape, and long-term durability. Only top-tier hides move forward to become garment-grade leather. Thickness determines performance. Too thin and the jacket lacks structure. Too thick and flexibility suffers. Premium jacket leather typically ranges between 0.9 to 1.2 millimeters. This balance ensures abrasion resistance while maintaining wearability. Precision measurement at this stage ensures engineering consistency later in production. American leather craftsmanship dates back to the industrial expansion of the late 19th century. Cities like Chicago and Milwaukee became early hubs of tanning innovation. Over time, the process evolved from vegetable pits and manual scraping to chemically controlled drum tanning systems. But one principle remained constant: material integrity determines product longevity. With grading complete, the hides move to the tannery, where chemistry transforms organic tissue into a durable, stable material that can last decades. In the next stage, biology meets industrial science. Collagen fibers will be permanently stabilized through controlled chemical reactions, a process that prevents decay while preserving flexibility. This transformation is what turns hide into leather. This is where organic biology becomes industrial material. Inside modern American tanneries, raw hides enter a precisely controlled chemical environment. The goal is simple in theory: prevent decay permanently. But the science behind it is deeply complex. Without stabilization, collagen fibers would decompose. Tanning restructures those fibers at the molecular level, locking them into a durable, flexible form. Collagen is a protein built from triple helix molecular chains. These chains are naturally strong but unstable when exposed to bacteria and moisture. Tanning introduces cross-linking agents that bind these fibers together. This cross-linking prevents microbial attack and increases thermal stability. In simple terms, the hide stops behaving like living tissue and begins behaving like engineered material. The hides are placed inside rotating drums filled with water and chemical solutions. Rotation ensures even chemical penetration. Without constant motion, tanning agents would concentrate unevenly, creating weak spots or inconsistent coloration. Mechanical engineering here directly influences chemical uniformity. Tanning chemistry is controlled by pH. For chrome tanning, the process begins in acidic conditions, allowing chromium salts to penetrate deep into the collagen structure. Then the pH is slowly raised. This basification locks chromium molecules in place. Precise pH control determines flexibility, strength, and resistance to heat. Chrome tanning is the most widely used method in modern American leather manufacturing. It is fast, typically completed within 24 hours, and produces soft, supple leather, ideal for premium jackets. The chromium ions create strong crosslinks between collagen fibers, dramatically increasing resistance to heat, water, and wear. An alternative method, vegetable tanning, uses natural tannins derived from tree bark and plant extracts. This traditional technique produces firmer leather, with rich patina development over time. However, for flexible garment leather, chrome tanning provides superior softness and lightweight performance. After chrome tanning, the material is known as wet blue, named for its pale blue hue from chromium salts. At this stage, the collagen fibers are permanently stabilized. The hide will no longer rot. It has become true leather, chemically transformed, structurally reinforced, and ready for refinement. Tanning stabilizes the collagen, but it does not standardize thickness. Every hide varies naturally. Some areas are thicker along the spine, others thinner near the belly. For premium leather jackets, inconsistency is unacceptable. To create uniform performance, the hide must be mechanically engineered to a precise thickness. The splitting machine uses a continuous band knife, a razor-sharp steel blade stretched across rotating wheels. As the hide passes through, the blade separates it horizontally into layers. The top layer, known as full grain, retains the natural fiber strength and surface integrity required for premium jackets. Proper feeding angle is critical. If the hide enters unevenly, pressure distribution shifts, leading to thickness variation across the surface. Modern machines use calibrated pressure rollers to ensure constant tension and uniform blade contact across the entire width. For garment-grade leather jackets, ideal thickness typically ranges between 0.9 and 1.2 millimeters. This balance ensures abrasion resistance while maintaining flexibility. Precision here determines how the jacket will drape on the body and how it will age over time. After splitting, the leather enters the shaving stage. Unlike splitting, which separates layers, shaving fine-tunes the surface thickness with micro-precision. Rotating cylindrical blades remove fractions of a millimeter, correcting micro-variations invisible to the eye but